Yeah, I think let's start with a welcoming word. So welcome to today's webinar about harnessing the power of Python tools. I'm very excited about this webinar. I'm not presenting myself. I'm Thomas Tellig, the Mac Plus product specialist. I have colleagues with me today who are much more experienced with coding and anything related to Python. Our presenter today is Ryan Walter Murray, working in data and what is your department?
Data and analytics.
Sorry, data analytics, and he's senior data and modeling engineer in Denmark. And as a supporter, we have Michael Yu, who is software developer and hydraulic modeler, and he's based in Canada. Before we jump right into the scripts and all the things you can do with them, some practical aspects. Of course, your microphone is muted, you can't talk, your camera is disabled. This is simply because we want to distribute the video at the end, and we won't avoid any issues with personal data. I hope you have entered your name all. The webinar will be recorded and made available to the public afterwards under the on-demand webinars. Please post your questions in the Q&A. I don't think you can use the chat anyway, but use Q&A, and we'll try to answer some along the way. And if you are not able to answer your questions, we'll come back to you. But before we start with the real agenda, we would like to know how experienced you are with Python. And I would like to ask you to join at menti.com. So simply open the webpage menti.com on your computer and use the code 789854449. I switched to there. Let's zoom. That's something else different. So that's the page, and actually it's live. So you should see what. Oh, it's very equally distributed, the experience with Python.
People are very quick too.
Yeah, we keep that open for. Well, we keep the screen open for the next couple of minutes if you're struggling to open Menti, but we wanted to get a first impression before I hand over to Ryan. Well, I would say we have some who haven't used it at all. Perhaps they get a taste of it today, and others where some have a bit experience and some have a lot. Yeah, and with that, I would hand over to you. I stop my presentation and please start your presentation.
Yeah, sure. Well, it's good to see that there's a pretty big mix of people.
Keep answering if you have opened. I mean, we'll publish the results at the end or with the PowerPoints.
Yeah. So could someone just confirm, am I sharing the presentation?
No, you're sharing the dashboard thing.
That's
click on the other screen, typically. Yeah.
Yes.
Yep.
Now we're good, yeah?
Mm-hmm.
Yeah.
Right.
Yeah, cool. So thanks a lot for coming. As Thomas said, I'm Ryan Murray, and I'm a senior data and modeling engineer at DHI. And today I'm going to show you a little bit about the Python packages that we have available at DHI, and you can start using these in your modeling workflows. So the brief outline for today, I would say first I want to start with, why Python? Why do you actually want to use Python instead of always doing things in a graphical user interface? I saw the distribution, some people are kind of using it, some people are experts, and maybe about a third of you, I think, had never used it. So this will give you some reasons of why you should put in the effort to learn Python. Then I'll go over the high-level overview of all the different packages we have at DHI. We call it the Python ecosystem. And then we'll hop into some live coding examples, and that's going to be most of the presentation. So why learn Python? I think there's many reasons. These are just a few that I have. So the first one is you can automate repetitive parts of your job. And I think that's very common in consulting, that we do similar projects, we have similar tasks, and Python is perfect for that, especially if it's involving data, which we're obviously working with all the time. It's a versatile tool in your modeling toolbox. So people use GIS, people use all sorts of things. You can think of Python just as one more tool to give you some flexibility to do something that maybe isn't included in Mike Plus by default. You can document and track your workflows. That's really good for quality assurance. If you have to write everything down in code, then you can go back to it. Someone can review it. You can do it again. So it's quite good for that. It gives some very powerful analyses and visualizations with the packages that are available. It's free and open source with a huge online community. Free and open source, I think, is a big benefit for businesses not wanting to pay for licenses. And then the huge community makes it very easy to go online and look up different resources for it. I would say it's the unofficial language of machine learning. You can make some machine learning models if you know Python. So, it's a transferable skill if you learn this. And then I would argue that it's fun and easy to use. So that's a good enough reason in and of itself. Okay, so how does Python fit into Mike modeling? So this is kind of how I think of modeling generally, and it's not just Mike modeling, but any model. So we start with some data. We do some pre-processing of that data. Maybe that's cleaning time series or fiddling around with, network, sewer networks and missing values and things like this. And eventually you get it into a Mike model, which could be thought of as a collection of different files. So a PFS file would be if you're using Mike 0. SQLite is Mike Plus. You probably know DFS 0 files, DFSU, etc. So all of these files collectively define a model configuration that we can then run. And then after you run it, you probably want to do some post-processing. We don't usually just take the model result and give it to the client. We want to work with it a little bit. So we do the post-processing, and then we arrive at some deliverable that I just call report here. So where does Python fit into this whole concept? I would say first, at the upstream end, it fits into getting the data. You can use Python to download data from, rain gauges if they have an API online, SCADA data if it's a wastewater treatment plant. Anyone that has an API, you can use Python to automate downloading that data. You can then use it to pre-process the data for the cleaning, etc. It's actually perfect for that use case. And then you can use Python to create models and modify configurations and run models as well. So you can use Python to automate some of this modeling process. And then in the post-processing, you can use it to create shapefiles, geotiff, do all sorts of different analyses. And then in the reporting phase, I would say it doesn't just have to be a PDF that we deliver to people these days. It could be a web app or something like that. and you can use Python to deliver those things. And it's easier now than it has been in the past. So yeah, as you can see, it's basically all the way through. So if you start learning Python, there's many different places that you can start using it. So at DHI, we have many Python packages. These are mostly organized based on what kind of file that you're working with, but they could also be organized based on what you're trying to do. So for Mike Plus modeling, I highlighted 5 packages that I'll go through here. The first one is called Mike IO. It stands for Mike Input Output, and it's for working with these kinds of files. The next one is called Mike IO 1D, same thing, but mostly for collection system modeling. And it's working with these kinds of files and more. Then we have Mike Plus Pi. That, of course, is for working with Mike Plus models, running them, changing the database, etc. Then we have a package called Model Skill. This one you can think of a great use cases for calibrating models. So you can compare the results of your model to an observation and calculate different fit metrics. And then another package is time series outlier detection. So you can think if you installed some flow meters in a sewer city, or not a sewer city, but in sewers across the city, sometimes the batteries run out and you get some bad data from the sensors. So you want to figure out how can I detect these outliers and take them out or consider them in some way. And that's what that package is about. All of these packages, we store them on the platform called GitHub. If you haven't heard of it, it's owned by Microsoft, and it's just a website for storing code, open source code primarily. Yeah, so that's where they live. All of these packages, I should mention, although we've created these at DHI, we're standing on the shoulders of giants because we're not starting from scratch. We're not reinventing the wheel. We're using a lot of other useful packages that already exist in the Python ecosystem. And these are made by scientists and engineers around the world. So I'll just mention a few here. There's Pandas, NumPy, Xarray, GeoPandas, SciPy, Jupyter, Matplotlib, sklearn, and probably many more. So I think it's worth understanding that there's a lot of useful packages in the Python ecosystem beyond DHI as well. And we recognize that and we build our libraries on top of it and try to make them work friendly with all of the other packages. So where can you go if you want to learn more about these packages? Of course, we're going to learn about it today, but afterwards, if you want to go learn about them, the first place I would recommend is going to our GitHub. So you can go to this link here, github.com/DHI. That'll have all of our Python packages. Within those packages, you'll get installation instructions included in the documentation. And there's also many self-paced notebook examples. If you haven't heard of a Jupyter notebook before, don't worry, because I'm going to use it a lot in this webinar. It's a very simple concept, and afterwards you can think back to this and say, oh, okay, there's many other of these examples that I can go find on GitHub. Also on GitHub, you can submit issues. It doesn't necessarily have to be an issue. It could be a feature request or some idea that you have, but it's a way of communicating with us So that's also possible on this platform. In a similar way, there's also a discussions tab. I saw there were some advanced Python users. You can also contribute code yourself to our libraries if there's something that you really think is useful and should be in there. You can do that because it's open source and it's not just ours, it's the public's. And then, of course, this is the first Python webinar, I think, at DHI, at least for Mike Plus, but there's going to be some more in the future, so just keep an eye for those. I guess Thomas will go over those. If you go to GitHub and you find one of our packages, it will look something like this. Here, it's an example of the Mike.io package. You'll see the name up here. We're in the code tab, so you see a file structure with all of the code. There's always a folder called notebooks, and that's where you go to find the notebook examples. There's also this issue tab that I mentioned and a discussion tab. A link to documentation that you can read. And if you were to scroll down a little bit, then you would find the quick, getting started guide. So that's it. Now I'll hop into some live coding examples. And I decided to do 5 examples. I don't have so much time, so they'll be sort of short, but hopefully give you an idea about what each package can do. Because not everyone's experts, I'll take it a bit slow and such, but yeah. So there's one example per package. Thomas, could you confirm, am I sharing the right screen still now? Or is it the Mike Plus model, or is it?
We see the Mike Plus user interface.
Yeah, okay. Let me change that. It'll be a bit annoying for me. So, okay. How was that?
Now we see Jupyter.
Yeah, okay. So Jupyter Notebook, it's just like a notebook that you can write in. You can think of it like that. You can also run code in these little cell blocks and get some responses back right away. That over there. So just as a example, say like 1 + 2 in this cell, run it, and then you get the answer 3. So that's what a Jupyter notebook is like. And then you can have all of this marked down. I have images, and you could think that you could use these notebooks to deliver a report to a client, for example, or as an appendix to your report. So anyways, the first model, Mike.io, the first thing that we want to do, this hashtag means it's a commented line. So it's just for me to remember the code, but I think I'll type it out. So we want to import the package. You always have to do that before you use it. And that means that it's now imported when we see this too. Now, if we want to open a DFS0 file, we would simply say Mike.io, I want to read file. And I have over here this data folder. So I can get some bit of auto completion. And here it's this 100-year rainfall file. And if I run it, what I get is a data set. So I can see how many different time steps there are, the start time, the end time, and all of the different items that are in that DFS0 file. So precipitation, its units. And what I can do is I can save that data set to a variable called ds. And then in different cells, I can use that variable to do other things. So in this cell, I plot it to see what it looks like. You can see it's just a Chicago distribution. We can convert it to a pandas data frame. I mentioned pandas was a Python library, and a data frame is like a table in Excel, you could say. So if I convert it to pandas and then into a data frame, and then this head just means show me the first 5 rows. We can see we would get this this nice table with the time index and all of our precipitation values. We can modify this table by using some basic math. So I want to make a new data set by multiplying the old data set by 1.4. And that's sort of maybe a climate factor, you could think of it. And what you would get is another data set with the values not shown here, but if you were then to plot it, you would see that the intensities are about 1.4 times the old intensities. And then we could just, with that data set, save it back to a DFS file called 100 year with climate factor.dfs0. And then I'll see it pop up in the folder structure over here. I'll just need to refresh. Yeah, so you see it's DFS0. So it's pretty good for handling DFS0 files. I think that's a great way to get into it. But it can do more than just DFS0. So now we have a DFSU file, which is like if you're doing a 2D coupled model, you would have that. So we'll again, mike.io.read. We want to read the data from the file. Here I use our Blue Beach example. I get this DFSU file. I read it. I'm going to save it again into a dataset variable. And here, so what's different from before? We still have the time axis. We see there's 121 time steps. We can see how many elements there are in the mesh in this DFSU file. We see the start and end time, some info about the geometry, and then all of the items that are in the file. So total water depth, the velocity components, and also the flux components. If we're interested in just one of those, like water depth, each one of these items, we can call it a data array. That's what DA is for. And you can just select them with this bracket notation. You get a list of these. And I select water depth. And now I get back a data array. Whoops. Its name is total water depth, and it has much of the same information as above here, except it's only for total water depth. Now I want to calculate the max water depth, and store it in a variable called DA_max. So the way I would do that is DA.non_max. And the reason it's non-max and not max is that you can have things that are not a number. That's what non stands for. And non-max, if there's nons across the time index, it'll still take the max value. Whereas if you just use max, it would automatically give you back a non if there's one non in that time index. Anyways, that's maybe a bit more advanced, but it's non-max. Now we've calculated this. We want to get a plot. So we'd say, hey, let's plot our data array. So we get our mesh. We have the C here, so it's very skewed. So we can change the color bar to be a maximum instead of 12. to be 0.3. And we just run the cell again. Now we get a better coloring. We can also change the colors to use blues instead of the default. And then we get something that's looking more flood-like. Working with mesh files is also possible. A DFSU file is basically a mesh file, but with results. So from that same DA_max, we can access the geometry, and then we can plot its mesh. Just why not? So we can see the mesh here. And then we can go ahead and save that mesh also using this toMesh function. Just call it mesh.mesh here. And then we have it saved here. I'll just delete these to keep it a little bit clean. You can also work with DFS2 files. I don't have a DFS2 file in this example. I thought it would be fun to convert the DFSU file into a DFS2 file, because that's sort of a common workflow. So the first way that you would do that, I'm just going to uncomment this. The DFS2 is a grid, so a rectangular grid. We need a grid, and we can create a grid based on the extents of the mesh geometry. And this specifies this, the width of the cells that we want. So dx equals 1 means give me 1 by 1 meter cells across the whole mesh extent. So then we get this 2D grid, but it's empty. It doesn't have any values. We have to interpret the max water level onto that grid. For the sake of time, I'm just not going to write this out, but run it. So now we interpret this DA max like the grid. And now we have a grid that's interpreted from the DFSU file. We can plot that grid the exact same way that we did with the DFSU file. And we can see that it looks basically the same, but the one up here was obviously very mesh-like, and this one is more gridded in this area. We could save that DFS2 file by using the toDFS method, and then specifying where we want to save it. And again, that's just going to save right here. And then if we wanted to get into a different format, like GeoTIFF, we could rely on a different library called Ryo X-ray. And what we do is we take our grid data array, convert it to an X-array format. We access the functionality provided by Ryo X-array, and it gives us the ability to convert that to a TIFF file. So yeah, there we have our TIFF file. So that's a very quick intro to Mike.io. It can do much more, but I think that hopefully gives a lot of ideas. The next one is Mike.io 1D. This one I mentioned is more for collection systems and also river modeling. Also water distribution. Yeah. So all of these sorts of files, you can use Mike.io 1D. And the way we do it is first, we have to import it. There's different ways to import things. You can either say import Mike.io 1D, or you can say from Mike.io 1D, import these specific things that I want. And here I want the ability to work with res1d files first. So I import that. And I want to have this variable called res. And in the data folder, I already have a few different results. One is for runoff, so the catchments, and the other is for the network. So we'll open up the network one first. That means it's open. We can print some high-level meta info about it. So again, we get the number of time steps, the start and end time, how many catchments there are, because this is just the network result, not the catchment, it's showing 0. But we have the number of nodes and reaches, and then all of the different items that are in here, and also their units. So to get this into a data frame, we can read it, and we get all of the quantities with the time into this massive data frame. But often that's a little bit heavy to use. You can see there's like 1,000 columns. So more often we want to go in to the network to where we actually care about. And you can do that in different ways. So if we say res.reaches, you can sort of interactively see, okay, now we have this result reaches. We can see all of the MU IDs of it. We can see which quantities there exist on reaches. And I should also point out that a reach can broadly mean pipe and canals, weirs, pumps. Basically any sort of link is called a reach. And that's for historical reasons, but it also works for river modeling. So yeah. So within this reaches, you can also get this neat auto completion that lets you search for, the item that you want. And then you can get that item and also see some attributes of it, how many grid points, start change, the length of it, etc. And also its quantities. And then if you want to get the quantities on that, you would just simply .discharge, .read. And now we have a much more manageable data frame than we did up here. It's just one column. If we don't want it as a data frame, we could also plot it. So, yeah. And then maybe we're not interested in one specific reach, but we're interested in the discharge on all the reaches. So we can still do the same thing, reaches.discharge.read. And now we get a data frame that is still less than 1,000 columns. I'm not going to plot this because I think it would take a long time to plot, but you could. And then you can also get some more nifty column headers that are sort of separated based on different aspects, the name and the chainage, etc. The same thing that applies for reaches applies for nodes. So here I have res.nodes, and I read a explicit node. See, there's one hand up. But maybe just write your Q&A and someone can tell me if it's relevant to answer now or after.
Yeah, Michael is already busy.
Okay, cool. Yeah. So after you read a data frame, you can also describe it, and then you'll get a lot of basic statistics for all of the elements. So you can get the mean, standard deviation, minimum, all the quantiles, maximum for all of the elements very easily. We can plot the network as well with the assistance of GeoPandas. And this one is just the network itself, but it doesn't have any quantities, but we could also add quantities on. I'm going to explain less the code because I want to get through the rest of the examples, and I see that time's running. So the same thing applies for catchment runoff. We can plot our catchments. And we can also export these things to shape files if you prefer to go use it in QGIS. Here we see all of the shape files popping up here. Just delete them again, keep it nice and clean. And then if you don't want to pop into GIS, you can also get interactive maps within a notebook itself. So this one's taking a little bit longer because it's downloading the base map. But you get this little interactive map, and you can hover over the links and see all of the different quantities here: max discharge, full velocity, etc. Aside from network files, you can also work with XNS11 files, which is the cross-section format. So you would say from MikeIO1D, import the cross-sections. You would open up the cross-section file. That confirms that it's open. And then there's different ways to select cross-sections. So on this X sections attribute, I can see there's 61 cross-sections. If I start getting some auto-completion, these are the, not the topo IDs, but the river names. We can also get the chainages, and then the topo ID. And the outcome of that is a cross-section that you get. You can also get an overview of all of them, similar to how you would maybe look in Mike Plus. Okay, I have all my location IDs, chainages, topo IDs, and we see there's 61 rows. We can plot our cross sections. So we have all of the bank markers here, left levee bank, lowest point, which it's not the lowest point, right levee bank. We can get the raw data. So here we have our markers, our X and Z coordinates, and the resistances. And also the process data that's actually used by the engine for the calculations. So flow area, etc. I didn't include it in this example, but it's also possible to modify these. I just thought it would take too much time. On to the next one. This is TSOD. We're going to fly through this one, I think, for time, but I think that I'll just focus on the outcome of the cells and just trust that you can learn the code later. Oh. So if you see some red, it's usually a bad thing, but it's easily fixed. So here I have some dirty data in a CSV file, and I read it into a pandas data frame. It's some water level, and you can see that there's something odd going on. So I can make a range detector to detect things outside of the range that I expect. Here I use -1 to 1. I'll skip the explanation for that and just go on to plotting these anomalies. So it locates where all of these anomalies are. And that's just, are they less than -1 or over 1? Very simple. There's more complicated ones. So there's one called the Hampel detector, which does uses some windows and some standard deviations. So we could, in the exact same way, use a different detector to find all of these things. While that runs, okay, there it is. So you see it's slightly different. We could combine the two with a combined detector. And then ultimately what we want to do is remove these anomalies. So we can use the NumPy library, and wherever there is an anomaly, we set it to not a number. And that would be our cleaned data series. So there's the result of the combined detector. And then we'll soon see the cleaned data set. Looks much better. And then we could save that into a DFS0 file using Mike.io. Ready for our modeling. Next one is model skill. This one is for, as I mentioned, like calibration. It can be used for calibration, but also just to evaluate the skill of your model, how well it matches some observed data. And I think I'll also go through this one sort of quickly. But the basic idea is first we have a DFS0 file with observation data and one with our model results. And in both cases, it's the first item in those files. And we create a comparison of those. So here we get our comparer. And this one has to do with significant wave height. We can plot the comparison. So we just want to simply look at how our model result is comparing with the observation. We can do that. But we can also have some more nifty ones. We can see exactly where rather not exactly, because these KDE plots are not exact, but we can get an idea of where the model in wave height is under or overestimating. There is box plots as well. Whoops. And also QQ plots. If we want some numbers, here we get a bunch of statistics like root mean square error, R squared, and many other ones. These are the short formed names, but you can easily go into the documentation to find these things. I put the link here for the metrics. And these are just the default metrics that are applied if you say .skill. But you can also customize that and write exactly what metrics you want. And you'll get the same thing with those metrics. This is using the whole time series, but often in collection system modeling, we're more concerned with events. So it's also possible to do event-based metrics. So here I have an event time series with my model and my observed results, and I mark these events. I make a comparison. And if I don't use the event first, we can see that many of the discharges are 0. So that's using the whole time series, and that's a bad thing. We don't really care about that. So we want to look only at when is there an event. So you could think of a combined sewer overflow. So now we have something more reasonable. This is only looking at the event portions of that time series. And we can see the model and the observations. In a similar way, we can get a skill table with all of the event numbers and their skills here. And then we can plot specific events. So it's actually not such a good fit here on the time series. And we can really, from the KDE plots, see that the model is under fitting because discharge is on the x-axis here. And then I'll skip the box plot. But that's the idea behind it. The last one, I'll go through this one quick, and then I guess there'll be 10 minutes for questions, which is fair. This is Mic Plus Pi. You can use it for running your Mic Plus models, modifying the database, and also using some tools in Mic Plus. I should mention that it's in an experimental stage, like it really experimental, not in the sense that we might scrap it because we're really committed to it. It's new. So that's what I mean by experimental. But anyways, it's still out there and you can go use it, and I think it can do some useful things. So here I show how to run a model. We would import some things. We would open our database using a data table access object. And here we can see what version of Mic Plus it is. It's only working with Mic Plus 2024 right now, so you would need that. To run a simulation, you create an engine object and say engine.run. And by default, it's going to run the active simulation. So now in the background, the model is running. It's a very small model. It's finished now. So using MicIO 1D again, I can plot the results of one of the links. I see that I get this discharge curve. I made it a steady state model that is just 50 millimeters per hour of rainfall over half an hour, I think. And just to give you some context for what this model is, it's super small. It's just a few pipes and a couple catchments. And link number 3, the plot that we looked at, is this link right here. So now let's modify it. We can change that constant 50 millimeters per hour to 25 with this number here. We have to know the table name, the MU ID, which column, and then the value that we want to use. You can get all of these values when you hover over the field in Mic Plus. It will tell you the table name and the column, usually. So we set that value, run the engine again, and then I'll plot the difference between the 50 millimeter per hour one and the 25 millimeter per hour. And it's already done, so we see, okay, it's checking out. Perhaps I mixed up the labels here, I guess, but you get the concept. And then if I want to run more than 50 to 25 millimeters per hour, it's Python, so we can just make a function to update this rainfall. It's the same thing as above, but it gives me a simpler way to do it in the rest of my script. I make all of these rainfalls, 5 millimeters, 25, 50, 75. And what I do is I loop over all of those rainfalls. I update the Mic Plus database. I run the engine. I open, using MicIO 1D, the result file, and then I plot it. So we can do that. And just 2 cells left, and then we're good for questions. This one's running 5 storms, so I guess it's takes a little bit longer. While we wait for that, okay, there we go. So now we can really see the 5 millimeter per hour, the 25, and we can see that eventually it's reaching the capacity of the network, which is why it's getting less and less. So then we could update the pipe diameters from, they were 0.3 meters to 0.6, and these are all of the pipe diameters, or sorry, the MU IDs. You could think of, okay, you could use this same logic to do some auto pipe sizing logic yourself. So what I did is I doubled the pipe size and then I rerun all of the same events. And these are simple constant rainfall events, but you could just as easy use a DFS0 file with an actual rainfall event. So it's up to you. I think it's pretty flexible.
Yeah, upcoming events. So we have some webinars related to Mic Plus and its application. It's a bit broader because the first already is about applying satellite technology for urban nature-based solutions, which comes out of our satellite technology department. So some inspiration about how to go beyond land survey. Then real Mic Plus webinar auto calibration for water distribution systems, sort of a first primer about the functionality we have now already, but I'll try to extend it slightly to steady state calibration too. Then if model skill caught your attention, there is a full webinar only about model skill, but be aware the exercises might be a bit marine or rivery, not really urban. Still, the library is applicable to all of these domains. And I think the final one is in May, understanding head losses at nodes in collection systems. This one will use Mac+Pi as well. So we have already a very nice script classifying manholes based on the connecting pipes. If you have any suggestions for Mic Plus webinars, please contact Evan, who is our Academy coordinator. I'd also like to mention the latest YouTube video about exploring the new water balance tools. It has been out for 3 weeks already. For some time, we have a training resources overview. It's a PDF under this URL. And if you click on these various icons, you'll see better. You get the full table of content of these either webinars or self-paced courses or blended courses. So thank you very much for your attention. If you enjoyed this webinar, please spread the word. We very much rely on word of mouth. And if you have any suggestions for training in general, contact Evan. And for this webinar in specific, contact Michael, because Ryan will be away for a couple of months. Good. I think that's it. I hope you enjoyed it. And hope to see you soon in one of our following webinars.